What is colossal magnetoresistance? Well, let's break down the word. Colossal means really big, and magnetoresistance has the word magnetic, sort of the same root word, and resistance, as in hard to get past. But the official definition is the change in electrical resistance produced in a current carrying conductor or semiconductor on application of a magnetic field. And that is what these materials, these thin films, are trying to display. So just to show you what one of the graphs look like, what we do is we hook it all up to a device, and you'll see that in a different one how we do the measurement, and we measure resistance as we heat it and as we cool it. So here's the temperature, here's the resistance in ohms going this way, and here's the temperature in Kelvin going across this way. And what we're looking for is the peak temperature here when it changes from an insulator to a conductor, and how steep the slope is right here, because the steeper the slope, the better the material. And we would like a peak close to room temperature because that will make it convenient for common applications. When we record the data, we also look for something called TCR, which is temperature coefficient of resistance, which is, there are some other things in the formula, but it's essentially the slope of this graph with a couple of factors in there for adjustment. And it's stated as a percentage out of 100%. So you can see in terms of a percentage, these are pretty low numbers because it's only up to 8.7, but that's typical for TCR data. And what's actually happening inside the material is if you have a ferromagnetic material, you can see all of the electron spins inside the material, or most of the electron spins inside the material, will line up nicely, right one next to each other, north, south, north, south, north, south. In an anti-ferromagnetic material, which is what this thin film normally is when it's not having colossal magnetoresistance, these manganites that we're using, is north-south, south-north, north-south, south-north. So you can see where anti-ferromagnetic comes from in terms of the name of the material. Now, the materials that we're using have rare earth metals, and we use lanthanum or neodymium or praseodymium with a manganite. Manganese is Mn, and manganite means it's combined with oxygen. These are antiferromagnetic because each adjacent ion behaves as a miniature magnet, and these align anti-parallel to each other, like I showed you in the last slide. Now, what happens when colossal magnetoresistance happens is you have a divergent alkaline earth metal, so something in that second row, like calcium for instance, will substitute in for the rare earth metal, which is a 3+. Well, when it does that, to balance out the compound, you can see here, the divergent earth metal substitutes in for the trivalent earth metal, the divalent alkaline earth metal substitutes for the trivalent earth metal, and that causes manganese to become 4+, but they won't all become 4+, some will stay 3+, and it's that electron transport between the 3+ and the 4+ that will cause the alignment of the electron spins, so the material becomes ferromagnetic, hence the colossal magnetoresistance. And at the insulator metal transition temperature, which is what we call that peak in the graph, ferromagnetic alignment becomes more energetically favorable than antiferromagnetic behavior, and it'll go with the more favorable situation. Because different ratios of earth metals, rare earth metals to alkaline earth metals produce different transition temperatures, Then you can design your own thin film specifically for your circumstances. When do you want it to change? How drastically do you want it to change? All that can be determined by the conditions under which the thin film is produced.